So for today's class, what we are going to do, now that we have talked about how to simplify radicals, so we did the following. We talked about how to simplify radicals. We talked about how to add and subtract radicals. Just like in fractions, you talk about first how you simplify fractions. You talk about how to add and subtract them. Now what we're going to do today is we're going to talk about what it means to multiply and what it means to divide radicals. So we're going to start off with the multiplicative property for radicals, and the multiplicative property for radicals says the following. It says that if you are multiplying two radicals together, and we're just going to call the first radical, I'm just going to give it a general name, I'm going to call that radical a times the nth root of b. And if I'm multiplying that radical by another radical, I'm going to call it c times the nth root of d. Assuming the index is the same, right? So we have the same index here, an index of n and an index of m. Then we define multiplication as follows. You multiply numbers on the outside of the radical together, they stay on the outside. You multiply numbers on the inside of the radical together, and they stay on the inside. Now, that's it. Of course, after this, then you have to make sure that you simplify everything completely. But this is the general idea behind multiplication of radicals. Again, assuming the index is the same, so this guy has to be the same. We multiply numbers on the outside of the radical together, and then we multiply numbers on the inside of the radical together. So let's do the following. Let's take a look at this first example, which says 3 squared of 6 times 5 square root of 3. Notice, first of all, that both of these are square roots, right? We have a square root here and a square root here, so we can multiply them together. We're going to multiply numbers on the outside of the radical together, 3 times 5, which is 15. And then we're going to multiply numbers on the inside of the radical together, 6 times 3, which is 18. Now, what I should mention is we're going to take a look at these on a case-by-case basis. So just like what we did with polynomials, we talked about how do you multiply a monomial times a monomial. How do you multiply a monomial times a polynomial? How do you multiply a polynomial times a polynomial? We're going to handle multiplication of radicals in exactly the same way. They act a lot like polynomials in that fashion. So for the mono times mono case, when we do the initial multiplication, we get 15 times the square root of 18. Now the last thing that you have to make sure that you do is that you simplify your answer completely. So let's talk about simplifying the square root of 18. So I'm going to think about 18. I'm going to think about all of the factors of 18. And then I'm going to think about the biggest perfect square factor of 18, which is 9, right? Because 3 times 3 gives us 9. So we can rewrite this as 15 square root of 9 square root of 2. And that's the same thing as saying, remember, we wrote it as the square root of 9 because we can simplify it. We know the square root of 9 is 3 because 3 squared equals 9, square root of 2. And so simplified completely, the answer to this is equivalent to saying 45 times the square root of 2 in its most simplified form. So the answer to that first one is 45 square root of 2. Let's take a look at a few other examples. Let's take a look at another example of a monomial times a monomial. Two terms, we multiply them together. Notice first that we have the same index, right? So we can multiply these guys. Notice also that this expression, the cube root of 4, doesn't have a number on the outside of it. So you can write a 1 there just to remind yourself that there really is 1. All right, so let's take a look. Negative 3 times 1 is negative 3. We multiply these two on the outside. We know we're going to have the cube root of something. We're going to have the cube root of 10 times 4, which is 40. So initially we end up with negative 3 times the cube root of 40. When we simplify that, what do we get? Well, the cube root of 40. Let's look for any perfect cube factors of 40. 1 and 40, 2 and 20, 4 and 10, 5 and 8. Are any of these guys perfect cubes? Again, it's possible that you can't simplify it any further, but sometimes you will be able to simplify it further. What do we think? Well, the cube root of 40, we do have a perfect cube here, right? Because 8 is a perfect cube. 2 times 2 times 2 gives you 8. So we can rewrite this as negative 3 times the cube root of 8 times the cube root of 5. And that's the same thing as saying negative 3 times 2 times the cube root of 5. And that's the same thing as saying negative 6 times the cube root of 5. So the answer to number 2, simplified completely, is negative 6 times the cube root of 5. Now we can't simplify the cube root of 5. 5 doesn't have any perfect cube factors. It's prime, so we're going to leave it alone. Let's take a look at one more example. Let's take a look at 5 squared of 6 times 2 squared of 3 times 1 squared of 2. And if you'd like to try, pause it, see what you can do with it. Okay, welcome back. When we multiply these guys together, so they're all square roots, so we can do this. 5 times 2 times 1 gives us 10 on the outside of the radical. On the inside of the radical, we have 6 times 3, which is 18. 18 times 2, which is 36, so we have 10 times the square root of 36. And then you say, okay, well, can I simplify the square root of 36? Well, that's the same thing as saying 10 times 6, right? The square root of 36 is a perfect square. 36 is a perfect square, so we can simplify the square root of 36 down to 6. And we get an answer of 60. So that's that, the product of those 3 monomials simplified completely. Well, let's take a look at some other cases. Like I said before, if you guys remember in regards to polynomials, we talked about monomial times polynomial, which is the second case, right? The first one we always do is a monomial times a monomial, which is what happens when you have 1 part times 1 part. And now we're going to do 1 part times many parts. And if you have a monomial times a polynomial, remember the idea is that we're going to distribute the term on the outside of the parentheses into each term on the inside of the parentheses. So we're using the distributive property here. And we can do that because these are all square roots. Square root of A, square root of A, square root of B, not a square root. And in fact, they're always going to be, under multiplication and division for this class, they're going to have the same index. We need some tricks from pre-calculus to talk about what happens if the index is different. Okay, so let's distribute. Let's multiply these two together first. 3 square root of A times 2 square root of A. Well, 3 times 2 is 6. Square root of A times square root of A is square root of A squared. Okay, so we distributed in that first guy. Let's erase this. Let's distribute in the second guy. 3 square root of A minus 3 square root of B. 3 times negative 3 is negative 9. Square root of A times square root of B is square root of AB. Okay, so we distributed that into the second term. Now let's distribute 3 square root of A into the third term. Notice that it doesn't have a radical here, so we're going to pretend like this is minus. This is 3 times 5, which is 15, but that's on the outside of the radical. And we only have 1 term on the inside of the radical, so we're just going to bring that over and call it the square root of A. Now, in regards to our answer, we have to make sure that it's simplified completely. This guy is not simplified completely, right? Because we could rewrite this here. This is the same thing as saying the square root of A squared, which is A, minus 9. Now, square root of AB, we can't do anything to simplify that, right? Each A and each B has an exponent of 1. The index is a 2, so if the exponent's more than the index, you can't simplify it. Same thing with this last term here. We only have 1 factor of A, so there's nothing we can do with it. So this would be what that expression looks like, simplified completely. Okay, let's take a look at example number 2. Okay, so for example number 2, same thing. We have a monomial. We're going to distribute it into a binomial. Notice again that all of the indices are the same, the indexes are the same. So we're going to distribute and we're going to distribute, and let's see what we get. So the first term, 5 times 2 on the outside of the radical, we get 10. We have an index of 3. 9 times 3 on the inside of the radical is 27. Minus next term. 5 times 4 on the outside of the radical is 20. Index of 3. On the inside of the radical, 9 times 2 is 18. So this is our initial multiplication, but then again, remember, now we have to go back and check and see if any of these terms are simplifiable. So 10 times the cube root of 27, well, the cube root of 27 is 3. That's the same thing as saying 10 times 3. Right? Remember, the cube root of 27 is 3 because 3 times 3 times 3 gives us 27. So that big gives us 30. Simplifying the cube root of 18. Well, let's look at all the factors of 18 and see if any of these guys are perfect cubes. 1 is a perfect everything, but again, it's annoying and it's never helpful in simplifying radicals. 2 is not a perfect cube. 9 is a perfect square because 3 times 3, but it's not a perfect cube. Neither one of these two are perfect cubes. So what that means is we don't have any perfect cube or higher factors of 18, so I can just leave it. I can't simplify that bit any further. And these guys, we can't combine them because they're not like terms. This is the answer simplified completely. So the idea when you're multiplying a monomial times a polynomial is you just want to make sure you distribute that term on the outside into each one of those terms on the inside using the property that multiply numbers on the outside of the radical together, they stay on the outside, multiply numbers on the inside of the radical together, and they stay on the inside. Okay, let's take a look now. Now this structure should look familiar. This is a binomial times a binomial. And I hope you guys remember, if you have a binomial times a binomial, we can FOIL. And you can do the same thing here too. Now again, remember FOIL just as mnemonic to help you remember to distribute. So when we distribute the first two terms in together, 2 times 4 is 8. Square root of 3 times square root of 3 is square root of 9. Those are the first two terms. Outer two, I'll do it with another color pen. 2 square root of 3 minus the square root of 10. Put a little 1 there just to remind myself there is 1. 2 times 1 is 2. Square root of 3 times square root of 10 is square root of 30. First two, outer two, oops. Inner two. Do that kind of another color too. Inner two. 3 square root of 5 times 4 square root of 3. So 3 times 4 is 12. And 5 times 3 is 15. And then the last two, do that guy in orange. 3 square root of 5 minus, put a little 1 there, minus 1 square root of 10. 3 times 1 is 3. Square root of 5 times square root of 10 is square root of 50. So here's what our 4 terms, right? And a binomial times a binomial, 2 terms by 2 terms, you know you should get 4 terms. But now we have 2 other things to do. First, once you get your answer, then you want to say to yourself, well, let me make sure I can simplify each one of these as completely as possible if they are simplifiable. For this first term here, 8 times the square root of 9, well, remember the square root of 9 is a perfect square, so that's the same thing as saying 8 times 3, and that's the same thing as saying 24. So this guy down here is the same thing as saying 24. Now, negative 2 square root of 30. Let's think about the factors of 30. 5 and 6. Are any of these guys perfect squares? Nope-y-dopey, 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 nope-y-dopey. No perfect squares. So there's nothing we can do to simplify that. So I'm just going to rewrite it as minus 2 square root of 30. 12 square root of 15. Let's think of all the factors of 15. 1, 15, 3, and 5. None of them are perfect squares either, so there's nothing we can do with that. So I'm just going to rewrite that as plus 12 square root of 15. Now let's look at minus 3 square root of 50. Ooh, okay, so minus 3 square root of 50. 50. 1 and 50. 2, 25. 5, 10. We're done. That's it. Any perfect square factors here? Sure. Square root of 25. So we can rewrite this as minus 3 square root of 25 times the square root of 2, because 25 times 2 gives you 50, which becomes minus 3 times 5 times the square root of 2, which gives us minus 15 times the square root of 2. So this is what we get when we're done simplifying each one of these terms. Now notice we're left with sums and differences. So the last thing that you want to do is you want to say to yourself, okay, can I combine any of these? Are any of these guys like terms? So go back and think about addition and subtraction. What does it mean to add and subtract polynomials together? Excuse me, what does it mean to add and subtract radicals together? Well, we can only combine them if the radican's the same. So here's a radical 2, here's a 15, here's a 30. This one doesn't even have a radical. So none of them are the same, so we can't combine them. So I'm just going to rewrite 24 minus 2 square root of 30 plus 12 square root of 15 minus 15 square root of 2. And this is what we get. This is what our answer looks like simplified completely. Okay, let's take a look at example number 2. Sorry, just checking to see what other types of examples we had left. For number 2, 3 square root of y minus 2 square root of x squared. You guys remember that? Remember that? Anytime you have anything other than a monomial being raised to a power, that means you're going to write out the expanded form. this is the expanded form. If you're multiplying something by itself, let's multiply it. If we're squaring something, that means that we're going to multiply it by itself. So, ready? First two, outer two, inner two, last two. First two, 3 squared of y times 3 squared of y. Well, 3 times 3 is 9. Y times y is y squared. That's the first two. Outer two, 3 squared of y, 2 square root of 10. So it's just going to be a minus here. 3 times negative 2, positive times a negative is a negative. 3 times 2 is 6. Yx or xy? I'm just going to put it in xy. I just like to see x first. It makes me more comfortable. Let's take a look at the inner two. Negative 2 times positive 3. Right, xy, xy. First two, outer two, inner two, last two. Negative 2 times negative 2 is positive 4. Square root of x times square root of x is square root of x squared. So this is the initial multiplication. And now again, when you're done multiplying, then we simplify and then we combine like terms. So let's see what terms in here we can simplify. Can we simplify the square root of y squared? Sure, remember there's a little hidden 2. If the exponent and if the index are equal to each other, that means you can simplify it. This is the same thing as saying 9y. The square root of y squared is y. Minus 6 radical xy minus 6 radical xy. Now you can't simplify the square root of xy. There's one factor of x and one factor of y, and those ones are smaller than the 2 as the index. Same thing with this guy. Plus 4, and the square root of x squared, again, 2 right over here. So if you have an exponent that's greater than or equal to the index, you can simplify it. And the square root of x squared is x. So the last thing we want to do, now that we multiplied it, now that we simplified each term, let's combine any possible like terms that we have here. But do we have any like terms? We have 9y. We don't have any other y terms. We have 4x. We don't have any other x terms. No. These guys, though, see this? Same index, same radicand. We can combine those. And you have negative 6 of something, and then you take 6 more away from it. That means we're going to be left with negative 12 of something. So for this example, simplified completely, we get 9y minus 12 square root of xy plus 4x. Try number 3. Try this one on your own. Okay. So, sorry about that. We're going to treat this guy the same way as we treated the one above it. It's a binomial times a binomial. So the product of the first two, 7 times 7 is 49, the first two. The outer two, 7 times 2 square root of 6. Now notice for the outer two here that there's only one term in the radical. These two, the 7 and 2, are on the outside of the radical, so we're going to call that plus 14 square root of 6. First two, outer two, inner two, negative 2 square root of 6 times 7 is minus 14 square root of 6. And then for the last two terms, negative 2 square root of 6 plus 2 square root of 6, well, what does that get us? So negative 2 times positive 2 is negative 4. Square root of 6 times square root of 6 is square root of 36. Okay, let's see what we can do to simplify each one of these guys. Well, 49, that's a regular rational number. We can't do anything to simplify that. Square root of 6, if you think of factors of 6, just 1 and 6 and 3 and 2. None of those are perfect squares, so we're going to leave that alone. We're going to call that plus 14 square root of 6. Same thing with this guy, minus 14 square root of 6. We can't do anything to simplify that. Minus 4 times, now the square root of 36, that's a perfect square, and we're going to call that minus 4 times 6. So we have 49, plus 14 square root of 6, minus 14 square root of 6, minus 24. And what do we get? Well, these two, look at this, 14 square root of 6 minus 14 square root of 6, these two cancel. We're left with 49 minus 24, which gives us 25. So the answer to this guy simplified completely is the same thing as saying 25. Okay, one more example, and then we're going to move on to division. We're not going to look at the case of a trinomial times a binomial or anything like that. You get the general idea in terms of how to multiply radicals together. Oh, okay, so we have the square root of x minus 1 plus 3 times the square root of x minus 1 plus 5. Now, when you're multiplying these guys, I really want you to think about this guy over here is one term. That whole thing is under the radical. This guy over here is one term as well. That whole thing is under the radical. So this is still a binomial times a binomial. All right, so let's see what we have when we have a binomial times a binomial. The square root of x minus 1 times the square root of x minus 1 is the same thing as saying the square root of x minus 1 squared. So that's for the first two. For the outer two, square root of x minus 1 times 5. So I'm going to call that plus 5 square root of x minus 1. For the inner two, 3 times the square root of x minus 1 is the same thing as saying plus 3 times the square root of x minus 1. And then for the last two, we have 3 times 5, which is 15. Okay, so that first bit tells us that we can rewrite this as the square root of x minus 1 squared plus 5 square root of x minus 1 plus 3 square root of x minus 1 plus 15. Now, what can we do to simplify this? Well, look, there's something that I didn't go over, but for sure you should be comfortable with this property that you can't break apart sums and differences. That is, this is not true. You cannot break apart sums or differences. So 5 times the square root of x minus 1 is not the same thing as saying 5 square root of x minus the square root of 1. You can't break them apart. But what you can do is you can simplify this bit over here. Now, remember, we have 2 factors of x minus 1, and it's a square root. The square root of any number squared, the square root of a squared is a, the square root of m squared is m, the square root of k squared is k, the square root of x minus 1 squared is x minus 1. These guys cancel each other out, so we're left with x minus 1. Square root of x minus 1 we can't simplify, square root of x minus 1 we can't simplify, so we're just going to bring these guys down, plus 5 square root of x minus 1, plus 3 square root of x minus 1, plus 15. Okay, anything else we can do to simplify it? Well, yeah, look, I mean, we have like terms here. These guys are like terms. Same radicand, they're both square roots. Same radicand, same index, they're both square roots. So we can combine those two. If I had 5 of something and then I add 3 of the same thing, we're going to be left with 8 of them. I'll just do this. And then I have 8 minus 1 plus 15. Excuse me, x minus 1 plus 15. So the x, we don't have any other terms with an x in them. So I'm just going to bring the x down, but we can combine the minus 1 and the plus 15, and that's the same thing as saying this. So be careful that you can have a polynomial under a radical as well, and that polynomial, the same properties for polynomials are going to hold for monomial terms. So what we're going to do, the last thing that we're going to do right now is we're going to talk about how we define division, and then we'll do a handful of examples of those. Now, I want you guys to understand that when we talk about division, we have 3 types of division in radicals that we're looking at in this class. There's other types of divisions in radicals, but we're going to look at 3 types in this class. We have division in the form where we have a numerator divided by a denominator, and the denominator is a radical. So it's something like 2 divided by the square root of 3. How would we divide those two? Well, we already talked about this, right? And we said, okay, you cannot have any radicals in the denominator. It's not simplified completely if you have radicals in the denominator. So we can do something like this, where you multiply the denominator by itself. That gives us 2 square root of 3 divided by the square root of 9. See this over here? And now the whole point behind doing that is we can get rid of the square root of 9 because the square root of 9 is 3. So this is equivalent to saying 2 square root of 3 over 3. These two are equal. However, there's no radical in the denominator. Remember, the ultimate goal is to get rid of the radicals in the denominator. So anytime we have a square root, you can do that. Now, what if we don't have a square root? What if we have a cube root? Take a look at 2 divided by the cube root of 2. Or a 4th root, or a 5th root, or whatever it is. Well, 2 divided by the cube, we still have to get rid of the radical in there. So 2 divided by the cube root of 2 is a little bit of a different animal. Notice that we only have 1 factor of 2. Remember, if it's a cube root, you need exactly 3 of them to take it out. So the trick behind this is we're going to introduce 2 more factors of 2, and that will give us a total of 3 factors of 2. Well, what are 2 more factors of 2? Well, 2 times 2 is 4. Okay, so where does that take us? It takes us here. Okay, now look, 4/8 will simplify down to 1/2, so it's equal to that. You can really see that here. But remember that the cube root of 8, the whole point that we're doing this, the cube root of 8 is the same thing as saying 2. So we end up with 2 times the cube root of 4 divided by 2, and you can do this on the outside of the radical together. You can cancel out those terms, and we're left with the cube root of 4. No radicals in the denominator. There is no denominator. It's actually not even equal to a fraction. And 4 doesn't have any perfect cube factors, so there's nothing we can do to simplify it. Okay, let's take a look at C. We have 2 divided by the square root of 3 plus the square root of 2. Right, square root of 3 plus the square root of 2. Notice, okay, monomial term in the denominator, monomial term in the denominator. How many terms do we have here? Hope you can see it. We have a binomial term in the denominator. Here's what we're going to do. Remember, ultimately, what we want to do is we want to get rid of all radicals in the denominator. So anytime we have a binomial term in the denominator, we're going to multiply it by something called the conjugate. Here's what the conjugate is. Now I'm going to go over this with you in another second, but I just want you to see why it works. The conjugate means you take exactly the same terms and you change the middle sign. So instead of calling this plus, we're going to call it a minus. Now remember that you have to multiply the numerator and denominator by the same thing in order for us to get equivalent fractions. So I have to multiply the numerator exactly by the same thing. Now, why does this work? Remember, what we want to do ultimately is we want to get rid of all of the radicals in the denominator. So now in my denominator, I have a binomial times a binomial. Square root of 3 times the square root of 3 is the square root of 9. First two. Square root of 3, positive square root of 3 times negative square root of 2 is negative square root of 6 for the outer two. Inner two, square root of 2 times square root of 3 is plus the square root of 6. Last two, square root of 2 times negative square root of 2, well, positive times a negative is a negative, and 2 times 2 is 4. Again, watch what happens. This is so exciting. Just hold on to the seat of your pants. Watch what happens here. Now, what can we do to simplify each one of these? Well, we know the square root of 9 is 3. We can't simplify the square root of 6. We know the square root of 4 is 2. Okay, and now what happens to the middle terms? We have minus square root of 6 plus the square root of 6. They canceled out. And in the denominator, we're left with just 3 minus 2, which gives us 1. Fantastic news. Look what we were able to do. When you multiply by the conjugate, that forces the first term to be a perfect square. It forces the outer term to be a perfect square. And it forces the middle two terms to be additive inverses of each other, so they will always cancel out. Now, this structure should look familiar, and if not, it's okay. But you guys remember that structure a minus b times a plus b? I remember what we get when we multiply a minus b times a plus b? We get a squared minus b squared. So those middle two terms, they cancel out. The first term's a perfect square, and the last term's a perfect square. That's why this property works. Now, we're not done with this guy, because this was a binomial times a binomial, but now we have a monomial times a binomial. So we have to distribute this 2 into the square root of 3. We have to distribute the 2 into minus square root of 2. And if you divide anything by 1, it's just going to stay the same. So this is our answer simplified completely. 2 divided by the square root of 3 plus the square root of 2 is the same thing as saying 2 square root of 3 minus 2 square root of 2, but it doesn't have any radicals in the denominator, so it's simplified completely. So again, when we divide radicals in binomial form, we multiply by the conjugate. Conjugate just means multiply by the same thing, but change the middle sign. So examples of conjugates. If I have something like negative 5 plus 3 square root of x, well, I'm going to write down the same thing, just change that middle sign. So negative 5 minus 3 square root of x. If I have something like 4 square root of a plus 2 square root of b, I'm going to write down the same thing, just change that middle sign, 4 square root of a minus 2 square root of b. These are conjugates. One more example of conjugates. If I have x minus y squared, it's called x minus y squared of 3. Write down the same thing, change the middle sign, x plus y squared of 3. This will always give us that structure of a minus b times a plus b. The middle two terms will cancel. The first term will be a perfect square, allowing us to get it out of the radical. The second term will be a perfect square, allowing us to get it out of the radical as well. Okay, let's put this into practice. Let's take a look at 3 more examples. We'll do number 1 and 2 together. So you look at the denominator, you say, okay, in my denominator, I have a binomial. I'm going to multiply the numerator and denominator by the conjugate. And the conjugate of the square root of x minus y is the square root of x plus y. Okay, so we're gonna have to FOIL the denominator. The square root of x times the square root of x is the square root of x squared. Square root of x times y is plus y square root of x minus y square root of x minus y times plus y is minus y squared. Now, again, watch what happens. The square root of x squared is x. Y square root of x minus y square root of x cancels. Minus y squared, we can just leave it. Oh, our goal is just to get rid of all radicals in the denominator, to find an equivalent fraction, but there's no radicals left in the denominator, and that's exactly what we did. We're left with x minus y squared. So now let's distribute in 3 square root of x times the square root of x and 3 square root of x times y. Remember, whatever you do to the denominator, you have to do to the numerator too. So 3 square root of x times the square root of x is 3 square root of x squared. 3 square root of x times y. 3 is on the outside of the radical, y is on the outside of the radical. Square root of x. Anything that we can do to simplify this? Well, sure, the square root of x squared is x. So we have 3x plus 3y square root of x. We can't just simplify that one factor of x. So this is equivalent to this, except we got rid of the radicals in the denominator. So remember, we talked about this before, but anytime we're dividing, it's the same thing as saying simplifying, rationalizing, dividing. The goal is to get rid of radicals in the denominator. Okay, 2 more examples. Let's take a look at 3 plus 2 square root of 6, 2 square root of 5 minus 1 divided by 3 plus 2 square root of 6. Well, let's first multiply by the conjugate. Conjugate means everything stays the same, just change that middle sign. Okay, now the denominators, because they're going to be in binomial form, we're always going to have to FOIL them. So 3 times 3 is 9, or distribute. 3 times negative 2 square root of 6 is negative 6 square root of 6. 2 square root of 6 times 3. 2 times 3 is 6 with the square root of 6 left over in the inside of the radical. And then for the last term, 2 times negative 2 is negative 4. Square root of 6 times square root of 6 is square root of 36. Let's see what happens here. What do we have? Well, these guys cancel. Those middle 2 terms will always cancel. We're left with 9 minus 4 times the square root of 36. The square root of 36 is 6. So we have 9 minus 24. And so our denominator is the same thing as saying negative 15. It's okay that it's negative. It's okay that it's negative 15. We got rid of all the radicals in the denominator. Now remember, whatever you do to the denominator, you have to do to the numerator too. So let's take a look at the numerator. 2 square root of 5 times 3, that gives us 6 square root of 5. Now, our numerator, I'm sorry, I forgot to mention this, our numerator is a binomial. The initial numerator is a binomial, and when we multiply it by the conjugate, that's also a binomial. So we're gonna have to FOIL this guy too. 2 square root of 5 times 3 is 6 square root of 5. 2 square root of 5 times negative 2 square root of 6, well, let's see, we get negative 4 square root of 30. Negative 1 times 3 for the inner 2, that's negative 3. For the last 2, negative 1 times 2 square root of 6 gives us plus 2 square root of 6. Now, let's see, is there anything we can do to simplify any of these guys? I'm bring over my negative 15 in the denominator over here. Square root of 5, we can't simplify that, and we don't have any other square root of 5s, so I'm going to write that as 6 square root of 5. Square root of 30, remember from before, 30 doesn't have any perfect square factors, so we're going to leave that as minus 4 square root of 30. And then what else do we have? Oh, I forgot to put the square root of 6 over here. Minus 3, no constant terms there, so we can't combine it with anything. And then negative 1 times negative 2 square root of 6 is plus 2 square root of 6. Same thing, nothing I can do with that. Look at this hideous mess. It is not beautiful, but it is the answer. So we got rid of all the radicals in the denominator. We don't have any perfect square factors in 5, 30, or 6. This is what our answer would look like simplified completely. Try one more. Try example number 3 and see what you can do to divide these two. Okay. So the conjugate of the square root of a plus the square root of b is the square root of a minus the square root of b. And whatever term we multiply the numerator by, whatever term we multiply the denominator by, sorry, we have to multiply the numerator by the same thing. Let's see what we get. Square root of a plus the square root of b, square root of a minus the square root of b. So the first two, square root of a times square root of a, square root of a squared. Outer two, square root of a times negative square root of b is negative square root of ab. Inner two, square root of b times square root of a is plus square root of ab. Last two, square root of b times negative square root of b is negative square root of b squared. Let's see what happens in the denominator. Well, these two cancel. The middle two terms will always cancel. Square root of a squared is a. Square root of b squared is b. Fantastic, we got rid of all the radicals in the denominator, which is exactly what we wanted. Now let's distribute into the numerator. Notice two terms by two terms, so we're gonna do the same thing. Square root of a times the square root of a. Square root of a times negative square root of b. Negative square root of b times square root of a, same thing. You can call it ab or ba. Negative square root of b times negative square root of b. Negative times a negative is a positive. So let's see what we get here. Square root of a squared is a. Negative square root of ab minus square root of ab. These guys are like terms. We can combine them, right? We have the same index. We have the same radicand. And remember, you can put a little 1 in front of here. So negative 1 minus 1 gives us negative 2. We have negative 2 of those square root of ab's. And our last term, square root of b squared is b. Now, some of you may want to do something crazy like cancel out these a's and b's and say the answer is negative 2 square root of ab. But remember, you can't do that because this is under addition and subtraction and not under multiplication. So this would be our answer simplified completely. Let me put that answer in a 3-dimensional box. And let's do this. Homework time. See you next class.